You know that smooth non-stick coating on your frying pan? Its creation involves an element so aggressively reactive that early scientists actually risked their lives, sometimes lost them, just trying to isolate it.
It's pretty wild stuff.
Yeah. So today, we're plunging headfirst into the captivating and often perilous chemistry of fluorine.
And we're really going deep. Our guide for this exploration is The Chemistry of Fluorine by T.A. O'Donnell. Specifically, we're looking at the foundational first 4 chapters.
The chapters 1 through 4.
Yeah, and this is volume 5 of the Pergamon texts in Inorganic Chemistry. It's a reprint from 1975 based on the 73 edition, so it's a really solid, time-tested source.
Exactly. So our mission today is to really get a handle on the fundamental chemistry of fluorine, from its dramatic discovery all the way through to the unique properties of its compounds. Think of it as building a solid foundation so you can appreciate why this element, often working behind the scenes, has such a huge impact on our world.
Sounds like a plan. Where should we start? Chapter 1.
Let's do it. Chapter 1 kicks off with the almost legendary story of fluorine's discovery, or maybe, more accurately, its isolation. It seems compounds with fluorine were known way before anyone could actually get the element on its own.
That's absolutely right. Things like fluorspar, calcium fluoride were known for ages, but getting elemental fluorine free, that was a massive challenge.
Why was it so hard?
Well, it boils down to its extreme reactivity, just incredibly reactive. Any attempt to liberate it from a compound would just, boom, instantly cause violent reactions with whatever else was around. Water, containers, electrodes, you name it.
So it was like a chemical Houdini. They knew it was in there, but trying to break it free just caused chaos.
Pretty much.
The book says 1886 was the year Moissan finally did it. What was his trick? What did he do differently?
Moissan's approach was really ingenious for the time. He used electrolysis, right? But on a very specific solution. Potassium hydrogen fluoride, KHF euro, dissolved in anhydrous hydrogen fluoride.
Anhydrous meaning completely dry, no water?
Exactly, bone dry. And crucially, he did this at a really low temperature, minus 24 degrees Celsius.
Okay, so dry and cold. Anything else?
Yes, the apparatus itself. He used equipment made of platinum, because pretty much any other material would just react, get eaten away by the fluorine as it was produced.
Platinum. Wow. So that specific combination, the solution, the temperature, the material, that was the key.
That was the breakthrough, yeah. It finally allowed him to isolate and actually contain elemental fluorine.
A real triumph of persistence and clever chemistry. Now, fast forward a bit. Fluorine isn't just some historical curiosity. Chapter 1 also talks about where we find it naturally and its surprisingly wide range of industrial uses. It's way more than just toothpaste, isn't it?
Oh, absolutely. You don't find elemental fluorine just lying around in nature, of course. It's far too reactive for that.
Right. But
it's actually pretty abundant in the Earth's crust, just locked up in minerals. The main ones are fluorspar, which is calcium fluoride, caurose, and cryolite, nihilapha.
And these minerals, they're the starting point for big industrial stuff.
They really are. Huge industrial processes rely on them.
Like what? Give us some examples that might surprise people.
Okay, well, think about aluminum production. That shiny aluminum in your cans or foil.
Yeah.
Cryolite is absolutely essential there. It acts as a flux.
A flux, what's that?
It basically helps things melt at a lower temperature. In this case, cryolite dissolves aluminum oxide and lowers its melting point dramatically, making the whole electrolytic process to get pure aluminum metal much more energy efficient.
Huh. I never knew that. Okay, what else?
Another major one is in the nuclear industry. Uranium hexafluoride, UF euro.
UF euro.
To enrich uranium for nuclear fuel, you need to separate the different isotopes, mainly uranium-235, from the much more common uranium-238. UF euros is a gas, even at relatively low temperatures, and the tiny mass difference between the isotopes allows them to be separated using methods like gas diffusion or centrifuges. Fluorine is key to making that volatile compound.
Wow. Okay, so aluminum cans and nuclear fuel. That's quite a range already. Anything else?
Then there's the whole world of organic fluorine chemistry, a massive field. Think Teflon.
Ah, the nonstick pan.
Exactly. Polytetrafluoroethylene, PTFE. Its incredible resistance to heat and chemicals, plus that super low friction surface, makes it indispensable for cookware, but also for seals, gaskets, cable insulation, all sorts of things.
Right. It's everywhere once you start looking.
It really is. And then historically, you had the chlorofluorocarbons, CFCs.
Ah, the ozone layer problem.
The very same. Initially, though, they seemed like miracle chemicals, inert, non-toxic, easily vaporized. perfect as refrigerants and aerosol propellants. Of course, we later discovered the devastating environmental impact.
A cautionary tale there.
Definitely. And finally, back to the perhaps more familiar use. Sodium fluoride, NaF. Added in small amounts to drinking water and toothpaste, it significantly helps prevent dental cavities.
So it really is an element with a massively diverse impact. But going back to the pure element, Chapter 1 also covers how we actually produce elemental fluorine today, industrially. Still tricky, I assume.
Oh yes, still very tricky. Not something you can just whip up easily. The basic principle is still Moisson's electrolysis, but on an industrial scale, it's usually done with molten potassium hydrogen fluoride, KHF0.
Molten. So hot.
Yeah, much hotter than Moisson's original setup, typically around 80 to 120 degrees Celsius. And maintaining that precise 1-to-1 mole ratio of potassium fluoride, Kf, to hydrogen fluoride, AHF, in the melt is absolutely crucial for it to conduct electricity well.
The book shows a diagram of a fluorine generator, right? Figure 1.
Yeah.
What are the key parts that let you safely make something so reactive?
Right. Figure 1 on page 1014, it shows a pretty robust design. Typically, you have a steel pot, which acts as the vessel and also the cathode, the negative electrode where hydrogen is produced.
Okay.
Then you have carbon anodes, positive electrodes where the fluorine gas is generated. A critical design feature is a barrier or skirt separating the anode and cathode compartments.
Why is that so important?
To keep the hydrogen gas and the fluorine gas physically separated, if they mix, well, they react explosively. So separation is vital for safety.
Makes sense.
And these things run on serious power. Operating currents are often in the range of 1,000 to 2,000 amps, maybe even higher in modern plants.
Wow. Definitely not a benchtop setup. Which brings us neatly to handling the stuff. Chapter 1 really hammers home the safety aspects for lab work. It's not friendly stuff, is it?
Not friendly at all. Elemental fluorine is exceptionally hazardous. You've got extreme reactivity, high toxicity, and it's incredibly corrosive. It reacts instantly with any moisture, even humidity in the air to form hydrogen fluoride, HF, and HF is nasty stuff, very corrosive, causes severe burns. Plus, fluorine itself boils at minus 188 Celsius, so it's a cryogenic hazard too.
So forget standard glassware then.
Pretty much, yeah. You need specialized apparatus. Materials like Monel, which is a nickel-copper alloy, pure nickel itself, copper, even magnesium can be used.
How do they survive?
They form a thin protective layer of metal fluoride on the surface. It's called passivation. This layer is inert to further attack by fluorine, so it protects the metal underneath.
Clever. What about glass? Can you ever use it?
Sometimes for certain things, but it has to be rigorously, meticulously dried first. Any trace of water is bad news.
Right.
The chapter also describes specialized techniques for handling volatile fluorides, often involving vacuum lines made from these resistant metals. There's mention of a backing valve principle developed by Caddy and O'Donnell, which is a clever way to handle reactive gases safely in vacuum systems.
And plastics.
Only very specific ones. Things like Teflon, PTFE, or KELF, PCTFE, are essential for seals, valve components, tubing, because they are highly resistant to fluorine attack. Figure 2 actually shows a KELF vacuum valve designed specifically for this kind of work.
It's amazing how the element's properties dictate the tools you need. Okay, shifting gears slightly, Chapter 1 mentions isotopes. Is fluorine mostly just one type in nature?
Overwhelmingly, yes. Natural fluorine is essentially 100% composed of one stable isotope, fluorine-19, or EF.
Just one? That's unusual.
It is quite unusual for elements of that atomic weight, but there is an important radioactive isotope, fluorine-18, UEF.
Radioactive. Useful.
Very useful, despite its short half-life, only about 110 minutes. It's a positron emitter, which makes it incredibly important in medical imaging, specifically positron emission tomography, or PE scans.
PE scans. I've heard of those.
Exactly. Here-office is incorporated into molecules like fluorodeoxyglucose, FDG, injected into the patient, and the positrons it emits allow doctors to map metabolic activity in the body, detecting cancers, studying brain function, things like that.
So even its unstable form is incredibly valuable. Okay, what about the basic physical properties of fluorine itself? Anything stand out in the data?
Well, Table 1 gives the rundown: atomic weight around 19, fairly low melting and boiling points, as we mentioned. But the really striking thing, considering how incredibly reactive it is the fluorine's single bond.
What about it?
It's surprisingly weak, weaker than the chlorine-chlorine bond or the bromine-bromine bond.
That seems backwards, doesn't it? You'd think something super reactive would have a bond it's desperate to break, meaning maybe a strong bond initially. Or maybe, wait, a weak bond is easier to break, leading to reactions.
The second part is closer. The weakness of the FF bond is actually a major reason for fluorine's high reactivity. It takes less energy to break that initial bond and get the fluorine atoms ready to react with something else.
Okay, so why is it weak then?
It comes down to fluorine's small size and incredibly high electronegativity. Each fluorine atom in the F0 molecule has 3 lone pairs of electrons. Because the atoms are so small, these electron pairs are crammed very close together.
Right.
And electrons repel each other. So you get significant repulsion between the lone pairs on one atom and the lone pairs on the adjacent atom. This repulsion effectively weakens the covalent bond holding the 2 nuclei together.
Ah, I see. It's like internal stress within the molecule itself, making it easier to snap apart.
That's a good analogy, yeah.
And that weakness leads directly into its chemical reactivity, which the book describes as, well, exceptional.
Exceptional is putting it mildly. Fluorine reacts directly, often vigorously, with almost every single element in the periodic table.
Almost. Any exceptions?
The only ones it doesn't readily react with are the lighter noble gases helium, neon, and argon. Everything else is fair game.
Wow. And the reactions are usually pretty energetic.
Oh, yeah. Highly exothermic, meaning they release a lot of heat, often very fast, sometimes explosive.
Explosive is always interesting. What kind of reactions are typical, like with metals?
With metals, fluorine tends to form metal fluorides where the metal is in its highest possible oxidation state. Its oxidizing power is immense. Alkali metals, alkaline earths, transition metals, it reacts with pretty much all of them, often forming fluorides that you can't easily make using other halogens.
And nonmetals.
Just as reactive. With hydrogen, it forms hydrogen fluoride, HF. That reaction can be explosive even at very low temperatures, even in the dark.
Yikes.
With carbon, it forms carbon tetrafluoride, CF0, and a whole range of other fluorocarbons, like the building blocks for Teflon. With sulfur, you get sulfur hexafluoride, SF0, which is surprisingly stable and inert, used as an electrical insulator.
SF, right. Heard of that one.
It even reacts with other halogens, chlorine, bromine, iodine, to form compounds called interhalogens, like CLFers, BRFU, ISER by 20 by 820 by 87. Fascinating structures.
And didn't you mention noble gases earlier? Reacting with them was a big deal, wasn't it?
Absolutely huge. For the longest time, noble gases were called inert gases because chemists thought they couldn't form compounds at all.
Right, they have full electron shells.
Exactly. But fluorine, with its extreme electronegativity and small size, was powerful enough to force the heavier noble gases like xenon and krypton into forming compounds. Things like xenon difluoride, SEF, or xenon tetrafluoride, XEF, even krypton difluoride, KRF arrow. That discovery back in the 1960s completely revolutionized our understanding of chemical bonding.
Just rewrote the textbook.
Pretty much. And the book emphasizes that fluorination, reacting something with fluorine, often pushes elements to higher oxidation states than you'd get with chlorine or bromine. It's just a much stronger oxidizing agent.
The ultimate chemical bully, maybe? But it's not all just violent reactions, is it? Chapter 1 also talks about biological activity, both good and bad.
That's a really important part, yes. The duality. On one hand, as we've said, elemental fluorine and many fluoride compounds, especially HF, are toxic and corrosive. Bad news if handled improperly.
Right.
But on the other hand, low concentrations of the fluoride ion, FO, have very well-established health benefits, especially for teeth.
The toothpaste and water fluoridation thing again.
Exactly. The book mentions the pioneering work by Dean and others who established the link between fluoride levels in drinking water and reduced rates of dental caries or cavities.
How does it work?
It gets incorporated into tooth enamel, forming fluoroapatite instead of the natural hydroxyapatite. Fluoroapatite is significantly harder and much more resistant to attack by acids produced by bacteria in your mouth.
Makes your teeth tougher.
Essentially, yes. Figure 5 in the book shows this relationship quite clearly. There's an optimal concentration, around 1 part per million, 1 ppm, in drinking water, that gives maximum protection with minimal risk.
Minimal risk, so there are risks with too much.
Yes. The book does note that very high fluoride intake over long periods can lead to problems like dental fluorosis, mottling of teeth, or even skeletal fluorosis, which affects bones. So, like many things, the dose makes the poison or the benefit.
A classic principle. Okay, finally for Chapter 1, it wraps up with analytical chemistry. Measuring this stuff must be tricky too, given how reactive it is.
It definitely presents challenges. Measuring elemental fluorine directly is very difficult because it reacts with your sampling equipment, your reagents.
Right.
So often indirect methods are used. But measuring the fluoride ion in solutions, like water, is more common and manageable, though still needs care.
What kinds of methods are used for the ion?
There's a range. Classical methods include gravimetric analysis, where you precipitate the fluoride as an insoluble salt, like calcium fluoride and CaReF, or lead chlorofluoride, PbClF, and then weigh the precipitate.
Okay, weighing stuff.
Then there are volumetric methods, titrations. A common one uses thorium nitrate solution with an indicator dye like alizarin red S. The fluoride reacts with the thorium, and the indicator changes color at the endpoint.
Titration, got it. Anything else?
Spectrophotometric methods exist too. These often rely on the fact that fluoride can bleach the color of certain metal dye complexes. The amount of color fading is proportional to the fluoride concentration. The zirconium alizarin method is a well-known example.
Using color change. Makes sense. Are there more modern techniques?
Absolutely. The development of the fluoride ion selective electrode, or ISE, was a major step forward.
I see.
Ion selective electrode. It typically uses a membrane made of lanthanum fluoride. This electrode generates a voltage that depends specifically on the concentration of fluoride ions in the solution. It's very sensitive and widely used, especially for measuring fluoride in drinking water.
That sounds very useful.
It is. And the book also mentions separation techniques, sometimes needed to isolate fluoride from interfering substances before measurement. Things like distillation as volatile hydrofluoric acid or a high-temperature technique called pyrohydrolysis.
Okay, that's a solid overview of Chapter 1. We've covered discovery, uses, production, handling, properties, reactivity, biology analysis. Quite a journey already.
It lays a good foundation.
Definitely. Now let's dive into Chapter 2, which is all about hydrogen fluoride, HF, as a solvent system. HF as a solvent. That sounds intense.
It is intense. And hydrogen fluoride is a truly remarkable and quite unique solvent. Its properties are dominated by incredibly strong hydrogen bonding between the HF molecules.
Hydrogen bonding, right. Like in water, but stronger.
Much stronger than in water. This has major consequences. If you look at Table 3 in the book, you see things like its boiling point, 19.5 degrees Celsius. That's astonishingly high for a molecule that small with only 10 electrons. Water boils at 100 C, but HF should boil much, much lower based on its size alone if it weren't for that intense hydrogen bonding holding the molecules together.
Wow, okay. What else does the hydrogen bonding do?
It leads to a high dielectric constant. That's a measure of how well a solvent can insulate charges from each other. A high dielectric constant means HF is pretty good at dissolving ionic compounds like salts because it can effectively shield the positive and negative ions from each other.
So it can dissolve things water can't, maybe?
It can dissolve different things, certainly. And it also leads to self-association. HF molecules don't just exist individually in the liquid.
What do you mean?
They link up through hydrogen bonds to form chains, even rings of multiple HF units linked together. Dimers, trimers, hexamers. Figure 7 shows some of these associated species. It's a very structured liquid in that sense.
Like a molecular network.
Exactly. And this structure is dynamic, constantly breaking and reforming.
Chapter 2 also mentions self-ionization. Does HF do that like water does? ADO making HOO and OK?
It does, yes, although to a much lesser extent than water. It undergoes autoionization according to the equilibrium. 2HF is in equilibrium with HOA plus IO.
HO, what's that?
That's the fluoronium ion, analogous to the hydronium ion in water, and IO is the fluoride ion, analogous to hydroxide in water's autoionization. The existence of these ions explains why even highly purified liquid HF conducts electricity slightly.
So it sets up its own acid-base system. Speaking of which, the book says HF is a strong acid in the gas phase, but acts like a weak acid in water. That feels contradictory.
It does seem odd at first glance, doesn't it? The key is, again, that super strong hydrogen bonding, but this time between HF and water molecules.
Yeah.
In water, HF forms such strong hydrogen bonds to the water molecules that it actually holds onto its proton more tightly than you'd expect. It doesn't fully dissociate, hence it behaves as a weak acid in aqueous solution.
But on its own.
But in its pure anhydrous liquid form, or in the gas phase, its inherent tendency to donate a proton is much stronger. In fact, anhydrous HF is what we call a superacid. Its acidity is incredibly high. The book mentions the Hammett acidity function, H0, which is like a pH scale for very strong acids. Anhydrous HF has a very, very negative H0 value, indicating extreme acidity, as shown in Figure 8.
So its environment completely changes its apparent strength. Fascinating. How do things actually dissolve in HF? What kinds of processes happen?
It's quite versatile. Chapter 2 outlines several ways. Some things, particularly certain organic compounds, might dissolve without really ionizing or reacting significantly, just physically dissolving.
Okay, simple dissolution.
Then you have dissociation. Many ionic fluorides, like sodium fluoride, NaF, or potassium fluoride, KF, dissolve and break apart into solvated ions. Now solvated by HF molecules and F solvated by HF molecules. Table 4 gives solubility data for various ionic fluorides.
Makes sense. What if the compound isn't already a fluoride?
Then you can get solvolysis reactions. This is where the solvent molecule itself reacts with the solute. It's analogous to hydrolysis in water. For example, some metal oxides or chlorides, when dissolved in HF, will react to form the corresponding metal fluoride, releasing water or HCl.
So HF actually transforms the substance.
It can, yes. And of course, you have straightforward acid-base reactions in the HF solvent system. Substances that can accept a proton from HF act as bases, forming their conjugate acid cation, which is then solvated by HF. Conversely, substances that can donate a proton to the HO ion from HS autohomogenization act as acids.
Like the Bronsted-Lowry definition, but using HF.
Exactly. And you also have Lewis acid-base reactions, where electron pair acceptors, Lewis acids, react with electron pair donors, Lewis bases, in the HF solution, often forming complex ions or adducts.
It really is a complex and active solvent. Does it support oxidation reduction reactions too?
Yes, it does. HF can be a medium for redox chemistry. Table 5 provides electrode potential data measured in anhydrous HF. These potentials tell you the relative tendency for substances to be oxidized or reduced in the specific solvent. Sometimes reactions that are difficult in water become easier in HF or vice versa.
It opens up different chemical possibilities.
Precisely.
The chapter also mentions other halogen fluorides as solvents, CLF here, BRR, IFU. Are they similar to HF?
They share some family resemblance, you could say. They're also highly reactive polar molecules capable of acting as fluorinating agents and as ionizing solvents. They also undergo self-ionization.
How so?
Well, for example, bromine trifluoride, BRS, self-ionizes to some extent. 2-BRF is in equilibrium with BRF plus BRF.
Ah, analogous to HF's HF and FAC.
Exactly. The BRF and the BRF anion. The book discusses how adding fluoride acceptors, Lewis acids, or fluoride donors, like alkali metal fluorides, can enhance the conductivity of these solvents by shifting these equilibria, as shown for BRS in Figure 11.
So you can make them conduct electricity better.
Yes, by increasing the concentration of the ions. And because these interhalogen fluorides have different reactivities, they can be used as selective fluorinating agents in chemical synthesis.
Selective meaning you can control the reaction better than just using elemental fluorine.
Generally, yes. They can allow for fluorination under milder conditions or lead to specific products. For example, you might use CLF for a vigorous fluorination, but maybe BRFUs or IFUs for something requiring a gentler touch.
Interesting. And they form complex ions too.
They do. You can form fluoranions like CLF, BRFR, IFR by reacting fluoride ion sources with the parent interhalogen fluoride. It's a rich area of chemistry.
Okay, that covers the unique world of HF and related solvents. Let's move on to Chapter 4, which surveys the fluorides of the main group elements. That sounds like a big tour.
It's a significant chunk of the periodic table, the S block and P block elements. This chapter gives a great overview of the sheer diversity in the properties and structures you find in their fluorides.
Diversity in what way?
Well, they range all the way from high melting point ionic solids like sodium fluoride to volatile molecular gases like carbon tetrafluoride or sulfur hexafluoride.
What determines whether it's ionic or molecular?
Primarily, it's the electronegativity difference between fluorine, which is the highest, and the main group element. A large difference, like with alkali metals, group 1, leads to very ionic bonds and structures. Smaller differences, like with carbon or sulfur, lead to more covalent bonds and discrete molecules. Atomic size also plays a role in the structure adopted.
Can you walk us through some examples group by group?
Sure. Group 1, the alkali metals,
Right.
Life, NaF, KF, these are classic ionic solids. High melting points, cubic crystal lattices, typical salt-like behavior. Table 6 shows melting and boiling points.
Okay, group 1 is pretty straightforward ionic. What about group 2?
Group 2, the alkaline earths. BF, MgF, KF, still largely ionic, but you start to see a bit more covalent character, especially with the very small beryllium ion, BF. A beryllium fluoride, BF, actually has a polymeric structure, kind of like silica, not a simple ionic lattice like Cap fluorspar.
Interesting. Group 13, the boron group.
Here we see a definite shift towards covalent bonding. Boron trifluoride, BF, is a planar molecular gas and a strong Lewis acid. Aluminum fluoride, alkali ore, is more complex. It's a high-melting solid with a 3D network structure, but the bonding still has significant covalent character.
Okay, and group 14, carbons group.
Carbon tetrafluoride, CF-ure, silicon tetrafluoride, CF germanium tetrafluoride, GFU. These are typically stable, volatile tetrahedral molecules with strong covalent bonds. Very unreactive, especially CF-ure. But interestingly, when you get down to tin and lead, their tetrafluorides, SNF-ure and PBF, tend to be solids with more complex, perhaps polymeric structures, and some ionic character creeping back in.
So it changes down the group too. What about group 15, nitrogen, phosphorus?
A real variety here. You have nitrogen trifluoride, a relatively stable trigonal pyramidal molecule. Phosphorus forms both PF-ures, similar shape to NF-ures, and the very important phosphorus pentafluoride, PF-ures, which has a trigonal bipyramidal geometry. Arsenic and antimony form similar pentafluorides, SFUs, SBFUs, which are powerful Lewis acids and fluorinating agents.
PFUs, trigonal bipyramidal. Got it. Group 16, oxygen, sulfur.
Well, oxygen forms OF-uros, oxygen difluoride, a V-shaped molecule. Sulfur gives us sulfur tetrafluoride, SFU, a seesaw shape, and the famous sulfur hexafluoride, SFUR, which is octahedral, exceptionally stable, and chemically inert, widely used as an electrical insulator. Selenium and tellurium also form hexafluorides.
SFUR is the super stable one.
Okay.
Group 17, the halogens themselves.
That's the realm of the interhalogen fluorides we touched on earlier, a huge variety. CLF, CLFU, CLFU,
Well,
BRF to BRFDF, ISFU, and even IFCO by E20 by 820 by 87. They have diverse structures, linear, T-shaped, square pyramidal, pentagonal, bipyramidal, often predictable using VFER theory.
Lots of different combinations. And finally, group 18, the noble gases.
The heavier ones, as we discussed. Xenon forms XF, XF. Krypton forms KRFS. Radon is expected to as well, but it's highly radioactive. These compounds prove that the noble gases weren't truly inert. Structures are generally linear, XS, square planar, XS, and distorted octahedral, XS.
It really is like fluorine unlocks the structural potential of the rest of the table. Now, Chapter 4 zooms in a bit on the ionic fluorides of groups 1 and 2. What's key there?
The emphasis is on their highly ionic nature. Strong electrostatic forces lead to high lattice energies, the energy holding the crystal together. This explains their high melting and boiling points, as seen in Table 6 again. They're generally hard, brittle solids. Their solubility depends on a balance between lattice energy and how well the ions interact with the solvent, the hydration energy in water.
Right, the balance determines if they dissolve. The chapter also mentions the inert pair effect for groups 13 to 15. Can you explain that again and how it affects their fluorides?
Sure. The inert pair effect is most noticeable for the heavier elements in those P-block groups, like thallium, group 13, lead, group 14, bismuth, group 15. It's the tendency for the outermost pair of s electrons, the SUT, to remain non-ionized, sort of held tightly by the nucleus.
So they don't participate in bonding as easily.
Exactly. This means that the lower oxidation state, which is 2 less than the group number, becomes more stable as you go down the group. For example, in group 13, boron is always +3, BFF, but thallium down below prefers the +1 state. TLF is more stable than TLF. In group 14, carbon and silicon are +4, CFF, but lead prefers +2. PZF is more stable and common than PBFF.
How does this affect the fluorides specifically?
Well, it explains the stability trends. TLFs is a much stronger oxidizing agent than BFs because TL3 wants to become TLI. It also influences Lewis acidity and structure. For instance, the pentafluorides, like PFS, SSUS, BFS, are common for the lighter elements in group 15, but bismuth pentafluoride, BFS, is extremely oxidizing because BIV prefers the +3 state due to the inert pair effect.
Got it. It explains why the chemistry shifts down those groups. Lastly, for Chapter 4, a quick mention of catenation in group 16 fluorides. Does sulfur form chains with fluorine attached?
It does, but not very extensively, especially compared to sulfur's ability to form chains with itself, like in SU rings, or with oxygen, like in polysulfates. The book mentions disulfur decafluoride, SA-urea, as an example. It has an SS bond with 5 fluorines on each sulfur. But generally, the high electronegativity of fluorine tends to terminate chains rather than encourage long ones. You don't see long SSS chains with fluorine caps like you might see with other groups.
Okay, so less common than in other sulfur chemistry.
Much less common.
Right then. We've covered a huge amount of ground discovery, properties, reactivity, the unique HF solvent system, and a tour of the main group fluorides. If you had to boil it down, what are the absolute key takeaways from these chapters?
I'd say first, the sheer, almost unbelievable reactivity of elemental fluorine, stemming from that weak FF bond and driving its entire chemistry. Second, the profound influence of fluorine's incredibly high electronegativity and its small atomic size. These two factors explain so much, from bond strengths and structures to its ability to stabilize high oxidation states and react with noble gases.
Electronegativity and size are definitely recurring themes.
Absolutely. Third, the fascinating duality how fluorine compounds can be hazardous but also essential, from industrial processes like aluminum smelting and UF production to consumer products like Teflon, and even the controlled use of fluoride ions for dental health. Fourth, the unique nature of HF as a highly associated superacidic solvent system with its own distinct chemistry. And finally, just the incredible structural variety displayed by the fluorides across the main groups, showcasing fluorine's versatility in bonding.
That's a great summary. It really highlights how those fundamental properties dictate everything else. So as we wrap up this deep dive, what's a final thought for our listeners to chew on?
Well, we've looked at the fundamentals laid out in this classic text from the 70s, but fluorine chemistry hasn't stood still. Think about where this knowledge leads today and into the future. Consider the ongoing development of complex fluorinated molecules for pharmaceuticals. Many modern drugs owe their effectiveness to strategically placed fluorine atoms. Think about advanced materials like new polymers or components for batteries and fuel cells, where fluorine plays a critical role. How might the unique properties we've discussed, the reactivity, the strong bonds it forms with carbon, its influence on electronic properties, continue to be harnessed to solve new problems in medicine, materials science, and energy? What undiscovered applications might still be out there waiting for this unique element?